a master student in cryptography. There's about lattices. And lattice is pretty I'll just give you what I'm doing. Lattice is pretty easy concept, but it's actually quite very hard. Lattice definition is lattice is a subset of Rn. It's a lattice of rank n if there exists b linearly independent vectors such that those generate the lattice. Yeah, there's just the definition of the lattice. Just we have d linearly independent vectors such that the integer coefficient, linear integer combination, and those vectors generate the lattice, and we call it this lattice. And in particular, if the number of vectors d is equal to n, we say it is a full rank lattice. And we also just, to make it simpler, we just say matrix, and we call this B, which is we just call it basis matrix of the lattice that generates it. That's pretty much it. There is a definition of the lattice. Just we all know the real coefficient linear combination. That's easy. Everyone knows that. But that lattice, you just all you gotta do is just change the coefficient into integer. That's it. That is the definition of the lattice. And of course, we need examples, right? And examples are also quite easy. Examples, for example, Zn, this lattice, because you can generate it by generated matrix is the identity matrix, right? Just anything pretty much. 300. There's pretty much one. Yeah, there is the Zn is lattice, example of lattice. Also, this is a lattice also, Dn, which we define it by lattice in Zn, such that the sum of the coordinates is 0 modulo 2. That is also a lattice. Well, if you want me to write a generating matrix, then it is there's the generating matrix of Dn. Yeah. And also another example will be An. Which is pretty similar, but even simpler than Dn, such that the sum of the coordinates is equal to 0, sorry. If there's a definition of An, and that is a lattice, because we have a generating matrix called -1, -0. So, yeah, we have three relatively easy lattices, examples of lattice, Zn, Dn, and An. And just I'll give you one more example of a lattice. Which is combines what we know. We just define it by dn plus the definition, which is the dn union dn. We just call that a set. There is a set. We don't know whether it is a lattice yet, but there is a lattice if and only if just any even. Yeah. There's a lattice. Well, I'm not sure about the matrix, generating matrix, but right now I'm gonna tell you how do we know whether a set is a lattice without finding a generating matrix, right? Yeah, but this is a lattice. But note that the shift of a lattice is not really necessarily a lattice. For example, Dn was a lattice, right? And lattice should contain a zero, always a zero by the definition of our lattice, because we can put all zero in the linear coefficient, it becomes zero, right? But this set does not contain zero. So this shift is not a lattice. But for some reason, if we union it with the Dn with the lattice, it becomes a lattice given that we have n is even. Yeah. So that was a quick example, but yeah, a little bit of work is required, and I'm going to show you how do we know this. It's too easy. This is the first proposition of the lattice. A subset, non-empty subset of Rn is a lattice if and only if it is a discrete subgroup of Rn. Do people know the discrete mean? The subgroup is pretty easy. It contains zero. If you add two elements, it still is in the set, right? And if you do the scaling, it's still. But the discrete is pretty new. But the definition of the discrete is.
Do you mean subspace?
Yes, pretty much subspace. Yes, but subgroup is better. And the discrete is, we say, a subset of L in Rn is discrete if is finite for every positive one. There's a definition of discrete. So what that means is pretty much on the grid, if you keep having an arbitrary number of big circles, the number of points of the set we are talking about is finite, right? There is the definition of discrete, that we say that set is discrete if we, for whatever radius of circle we put, the number of points in the set is finite. That is the definition of discrete. Not all sets are discrete. So yeah, the important part is this proposition, but unfortunately, unlike the definition of a lattice, this proposition is quite considerably takes time, a bit of time. It's not too deep, but it still takes time. So yeah, I recommend go with this because the definition of lattice was easy, but this one is pretty. Yeah, you have to think a little bit. But the thing is, from here we can make problems that is actually used in cryptography lattices. Because of the discreteness, what it means is that we have a shortest vector in the lattice. because this is discrete, we have a shortest vector. There exists a shortest vector. Because considering 2D, we are thinking about 2D because 2D is just an example that we can draw. It's kind of, there's lattice points kind of just many there. This is an example of this. Lattice, for example, say, and we still have many points above. And the reason that we have a shortest vector is that consider we draw a circle, large enough circle like that. And by discreteness, there's a finite number of points inside the circle, right? The discreteness, yeah, we proved. Discreteness. So that means because of the finiteness, we can actually try computing all the distances from the origin. That's possible, finite, right? Finiteness. And then we can just choose the minimum one. And that will be the shortest vector, right? So that's why we have a shortest vector. You know, like, we don't really have that kind of concept because, you know, in the real number, for example, 0 and 1, what is the positive number that's closest to 0? That doesn't exist, right? I mean, 0.0001, 0.001, there are too many. So in this case, we have a shortest vector in the lattice. That's the point of discreteness. We have the shortest vector. And finding a shortest vector in the lattice, given a lattice, is actually quite hard. There's no really known algorithm for that, given that you have a generating matrix of the lattice. As a hint, you can't really solve it. So it's pretty hard. And also, the thing is, what the lattice is that we can just move this circle. I mean, the definition of the closest vector problem is still the same. For example, you are given a point that is not on the lattice. Lattice is this point, right? Circle points. And you're given with this x point. And you want to find what is the closest lattice point to this x. Given you know this x. What is the closest vector? I mean, again, we have to prove that does there exist the closest vector in a lattice that is closest to t? Because again, it may not exist, but by the discreteness, pretty much the same. But you need to prove this rigorously. But because I don't want to do rigorous here, I just move this circle to the point of x, just point of x, and still is conserved. The discreteness is conserved, even though it's not origin. There's still a finite point if you have some sufficiently large circle at the center x, then inside circle there's a finitely many lattice points inside it. So again, you can compare the you can choose the one that is minimum distance. So that problem is again hard. There's no known algorithm that is really efficient. I mean, solving very quickly. And this kind of problem we say is closest vector problem. This is CVP, called CVP. And this is shortest vector problem, SVP. Yeah, so there are many journals that try to come up with the algorithm of, you know, given a lattice and its generating set, how to find the shortest vector, or how to find the closest vector to a given vector. You know, it's actually pretty challenging, actually. But there's some attempts has been going on. There's some, you know, like this kind of method. There's some journals where you kind of choose an appropriate radius with a circle, and you somehow try to efficiently filter out that is the closest one. But unfortunately, when we make an algorithm, we also have to consider the running time. Running time is complexity, right? The number of steps that you have to carry out in order to get the correct answer. And there are many kind of algorithms, not many, but kind of few algorithms that actually does the right thing of output, right? But it takes too long. For example, the complexity is kind of if in a lattice of dimension n, the complexity to solve CVP or CVP is kind of this messy number. It means like pretty much in worst case, you have to carry out n to the power of something messy number of n to get the right answer. And unfortunately, this thing is even bigger than the exponential. Exponential time complexity is too much. You have to carry out too much. And if you want to put in the software, the computer will pretty much go out. So what you want to do is to make it somehow complexity into polynomial time complexity. Like the complexity equation should be in form of something like, n squared, n5. This kind of complexity. The polynomial complexity is what we actually really aspire to achieve. But yeah, so far there are most of algorithms are known to be this more than exponential, which is kind of really infeasible to carry out, even though they give a right output someday. But the good news is the examples that I've shown you, like the easy examples of lattices, they don't even need a definition of lattice to be solved for ZN. ZN is, I think you can do the closest vector problem. This is very easy. Because, for example, I can give you this is given vector. And what is the vector lying inside Zn that is closest to T? The answer is just round this up. Closest rounding. 0.3 is closest to 0. 1.4 is closest to 1. 2.7 is close to 3. And minus 0.4 is closest to 0. And there's the answer to this closest vector problem. That's it. You just round each entries to the nearest integer. And some book says, if you have a tie, what happens? 2.5. Do you round up to 3 or do you round up to 2? And pretty much they give the same answer for that entry, but sometimes they want to find what is the closest vector of least norm. And the least norm, then you have to round up to 2. So that gives the absolute value is less. But that doesn't matter. This is really easy. Just round it up. No algorithm required. You don't even need a basis. Yeah. But as you might expect, Dn is kind of a bit confusing. For example, what is the vector closest to? You have to think about this a little bit. And yes.
Dn? What are you trying to get?
Oh, we're given with this point, and what is the vector lying inside Dn that's closest to this vector? Yeah, the answer is, this is the bad example, but the answer is 0, 0, 0.
Is it 0, 1, 2?
Pardon?
It's 0,
Yeah,
1,
mode 2, yeah. Oh, sorry, mode 2. Yeah. And what else? We are now thinking Z3, that's 3 dimension. What will be the closest vector?
One, two.
1, 2.
And
1.
Oh, 0.
0. This one. But this doesn't lie even in the set because 1 plus 2 is 3. And 3 is not 0 or 2.
1, 2, 3.
1 to 3. 1 to 3 seems to be on D3. Yeah, see this right. What you do is, okay, so the closest number to the 1.3, I mean the integer is 1, and 2.1 is 2, and 3.7 is 4. But the algorithm DN, you have to compute the difference between these two numbers and choose the smallest, the one that gives the smallest difference. And in this case, actually, sorry, the biggest difference. Sorry. In this case, it's 0.3, right? Because 2.1 and 2 is only 0.1 difference, and 1.3 is 1.3 and 1 is 0.3, and 3.7 and 4 is 0.3. So we can actually choose any one of them, but because you chose the last one, I chose 4. And then what you do is you wrong way round it. Instead of putting 4, you just put 3. And that is pretty much the algorithm of the end. Just kind of choose the entry that gives the largest difference between the number and the closest integer. And wrong way around it, not the closest, wrong way around it. And that's the answer. And unfortunately, the proof of this is a little bit harder than Zn, because you kind of have to muck around with the condition mode 2, and it's still doable. Yeah. It's not hard. Just it takes more time than Zn. I did an example. I showed you that the known algorithm for a long time was n to the power of n, the complexity to solve it, right? But luckily, I think it was 2009 or 2000, they reduced it into complexity got reduced into some very negligible amount, maybe very like 0.05 n, something like that. Still big. But under this method, even though the journal that has reduced the complexity to this didn't really do much, or I'm still brilliant, but still not too much, right? But the method was kind of really helpful, so that in 2009, somebody actually had reduced it up to 2 to the power of n. This is much better, because in n-dimensional, this can give 100 to the power of 50 complexity, whereas this is just 2 to the power of 100. That's much lower. Yeah, so there is a reduction in the complexity, and that's what all these people is really interested about, reducing down the complexity of the algorithm. And yeah, I just want to show you how they have done that. But I just had to make a little bit of definition. There's a thing called Voronoi Cell. In this paper, when the journal had reduced the complexity to this one, it used the Voronoi cell, the concept of Voronoi cell. And then later, in 2009, somebody developed this concept, the Voronoi cell, to bring it down to this complexity. So the Voronoi cell is at the heart of the reduction of the algorithm. So we define the Voronoi cell of a lattice to be. It's pretty easy. Everything is easy. So the Voronoi cell is a set of points that is close to the origin than any other lattice points. So what it means is if you have lattice like that, the Voronoi region is kind of like that. This is the Voronoi region. Because any point in this region is closer to the origin than any other lattice points. This is the definition of the Voronoi cell. The set of points that is closer to the origin than any other lattice points. That is the definition, and this is the Voronoi cell. And of course, because of the characteristic of the lattice, this gets copied to every different lattice points. So it's kind of identical. This shift. There is a Voronoi cell. And one thing to notice is that this is symmetric. Meaning that if an element is in the Voronoi cell, then minus that element is also in the Voronoi cell. And this is also convex. So if in a Voronoi cell, if you choose any point in a Voronoi cell, and the line joining it is also contained in the Voronoi cell. It's a complex. And also, one thing that is pretty important is, the definition of the Voronoi cell is equivalent to the intersection HV, where HV is HV is just expect for every lattice you define HV into that, and then by the definition you can just describe the Voronoi cell as intersection of all of HVs where V is non-zero lattice points. There's the alternative definition. But the thing is, there exists a minimal set of lattice vectors, finite. There exists a minimal set V of the lattice such that what it means is, in the definition, it seems that we have to get the intersection of every lattice vectors, non-lattice vectors, right? But the thing is, we can prove that there exists a finite set in the lattice such that the intersection of them generate the Voronoi cell. And that's pretty important because I'll give you an illustration. This is a lattice point, and this is 0. And say this is V1. What will be the region HV? Well, try to join origin and V1 and choose the midpoint. And you do the perpendicular bisect. And every region under this is a HV. It's pretty easy geometrically, you know. If you log this line is close to V1, if you log this line, it's closer to origin, and the HV is the point that is closer to origin than V1. So that is the HV1. And you do similar for V2, for example. V2, that will be HV2. You kind of clearly see that the Voronoi relevant vectors of this kind of lattice is only 6 points. This one, this one, this one, this one, this one, this one. So, if you draw another diagram. The Voronoi cell looks like like that. And these are relevant vectors of this particular lattice. Because if you try to do HV for any other lattice, I mean, there's a big region and this is still contained inside that region, right? So the Voronoi relevant vectors are only six of them. And with that, by slicing, you get the Voronoi cell. That's why we call it slicing. Slicing. You just kind of slice it, 6 times, and you get that. And in a dimension n, for any lattice, the number of Voronoi relevant vectors, and these are the Voronoi relevant vectors. In dimension n, the number of is bounded above by 2 to the power of 2n minus 1. There's a theorem, so this is clearly finite, and you cannot have movement. See, like in this case, it was 2-dimensional, right? So n was 2, and you put it inside here, and this is 2 times 3, 6, right? Yeah. So this lattice 1, 2, 3, 4, 5, 6. Yeah, 6. It gets a maximum number of Voronoi relevant vectors. Questions? Is there any questions? So the definitions is not really hard, but because it's going a bit fast, it's a bit hard to digest. You can give an alternative definition to V. Voronoi cell of vectors are n. So the dot product is this characteristic of a Voronoi relevant vectors. If you take any arbitrary V in V, big Voronoi relevant vector, and if you dot product it, the absolute value satisfies this condition. There's another variant of the definition of Voronoi relevant using the Voronoi relevance set. And one thing that I actually need to emphasize is that, you know, that we have made a Voronoi cell, right? Just something like that. So if the problem asks you, given that if you have a point in something given point t, what is the closest lattice vector to t, then the problem is converted into finding a Voronoi cell. Because if once you're in the Voronoi cell, if once this point is Voronoi cell, then the closest vector problem is done by saying that the answer is origin. And other cases also similar. You have to somehow locate the Voronoi cell closest to the given lattice. And the problem is the Voronoi cell tiles the whole space. It is a disjoint union and it fills out the whole space. So if you're given with any lattice vector t, then that t will be contained in some lattice point. Some Voronoi cell of some lattice point. It might be origin or it might be some. If you have x, it will be contained inside like that. So if you find the Voronoi cell, then you will be able to find this. So the problem is pretty much about finding a Voronoi cell, locating the given point to some Voronoi cell, locating the given point in some kind of Voronoi cell. But what is that Voronoi cell? And yeah, you kind of have to do the slicing illustration that I showed you to find the Voronoi cell. But yeah, it's not too hard. It's easy, but the thing is the complexity was too much. It was more than exponential. So what in 2010, what other guy did was to use that idea to develop. I mean, pretty much what it means by develop is you do more study about Voronoi cell. You know more properties about Voronoi cell, then so that you can have the complexity lower. But this idea, the Voronoi cell idea, was pretty novel. It was 2006, and that was the new technique to solve that. But complexity was not that high, even though the journal said that his complexity is better than any others. But the complexity was pretty much negligible, like the difference is still pretty much same. But it was good that he used the Voronoi cell idea, so that the other guy later improved to exponential. But still, we don't really expect it to be polynomial, but it will be a big breakthrough that if we find the polynomial. So the thing is, the current known complexity is 2 to the power of n.
Okay, thanks. We have the lecture.
Yeah, good. I'm sorry. There is this. Yeah, the known algorithm is complexity step. There's a main takeaway, and somehow try to reduce that. Yeah. Thank you. Sorry.
That was good.